Hello and welcome to the CS4 interview. Joining me this week is Kenny Smith from the University of Edinburgh, who's going to be talking about the biological and cultural evolution of language. Hello, welcome.
Hi.
Thanks for coming. Okay, I can imagine that if you're interested in how language has evolved and how it's used, that it's a potentially multidisciplinary activity. So it could be from anthropology, biological evolution, maybe even neuroscience. You've got a bit of a mixed and really quite interesting background, because some of the earlier work you did was more similar to artificial life type simulation activities. So can you tell me, how did you get into doing the kind of research that you're doing now?
Yeah, so I was an undergraduate at Edinburgh University and I was doing a degree in linguistics and artificial intelligence, and I was thinking I would probably get a job afterwards doing natural language processing or something like that, and I wasn't very excited about it. And then I went to a course by, just an undergraduate course by Jim Herford and Simon Kirby. So Jim's a retired professor at Edinburgh, Simon Kirby's a professor of language evolution at Edinburgh, and they were running a course on basically simulating language evolution. So using computer models to try and think about how communication might evolve, how languages might evolve. And I went to that course and it was just brilliant. It was the most exciting thing I'd done at university. So I did my undergrad dissertation with those guys, and then came back to do a PhD and then postdocs, and now I work with Simon and Jim.
Okay, so what's been the role of simulation then in your particular research interests? I mean, put it this way: what would is there a typical evolution of language simulation? I mean, what would it look like?
Yeah, so we started out doing simulations. So basically, Jim Herford was the guy who pioneered doing computer simulations for language evolution. So in 1988, 1989, he had a paper which was about, it was called Biological Evolution of the Saussurean Sign. But the idea was that we don't have any. The claim was that we don't have any good evidence about how languages evolved, and we can't go back and study it, and language doesn't fossilise and so on. So the best we can do is kind of to simulate how communication systems evolve, and under what conditions do you get these bidirectional communicative kind of signs like words in languages. So Jim had that paper, and then 10 years later Simon Kirby was working with Jim and had another paper on how a simulation model of how syntax might evolve, so how you might evolve a system where you don't just have words, but you combine words into these kind of complex utterances. And so at that point, the simulation stuff was basically, it was all we thought we could do to study language evolution. So we can't go back and study it. We can't study the evolution of language in humans, but we can study the evolution of language in simulation. So we can see how languages might evolve, and then we can try and extrapolate and see maybe if we can understand how communication systems and languages in general evolve, maybe some of those ideas will apply to how human language evolved. Recently we've kind of made a bit of a move away from simulation. So we've realised that actually you can do what people normally think of as a simulation, which is a computer-based simulation, that you set up some artificial agents and you have them doing something, so that you have them learning a language from each other and maybe communicating and adjusting how they communicate, and you can see how their languages evolve. That's a kind of standard agent-based simulation. But you can also do human-based simulations, so you can run experiments with real human participants where you set up some set of conditions. You have people learning language from each other, using a language in a very constrained set of a very constrained language, a very constrained set of kind of possible interactions they can have, and then you can see how languages evolve in those many kind of laboratory populations of humans. So basically, one way of thinking about the experiments that we do is that it's just basically simulation, but instead of using a computer model of a communicating learning agent, you use a physical instantiation of a communicating learning agent, a human.
All right, so that's quite cool, because you've almost like come, not full circle, but you started off thinking that you need simulation because you don't have the empirical data.
Yeah.
Like you haven't got a time machine, so we can't go back and see how Neolithic people were talking to each other. So let's think about filling that kind of data gap with simulation.
Yeah.
But now you're actually using humans almost in the same way that you would use simulated agents?
Yeah, absolutely, yeah. Okay. So under a given set of conditions, where there's such and such a constraint on transmission, people have to use their language for performing particular tasks. How does the language evolve? How does the language itself change and adapt to those kind of task requirements? And you can ask those questions with a simulation model, or you can ask exactly those same questions in the experiment lab with human participants.
Okay, so how do they compare in terms of agents, a simulated agent and an experimental subject? I guess I'd be interested to know, the pros and cons of using, real people or simulated agents. But in terms of utility or usefulness, I mean, if you use humans in exactly the same way as you use the simulated agent, then that maybe doesn't seem to be offering a great deal. So what
no, so the advantage of simulation is all stuff you know, right? So you know exactly what's going on in the model. You know what the simulated agents, what they can do, how they behave. And so the point of running the simulation is just to find out the kind of outcome of the complex interactions between these agents. You might get some kind of emergent effects that are a consequence of interactions between multiple agents. Mm-hmm. With these kind of the human-based experiments we run, we don't know so much about how the individual agents work. So you don't have access to how people work, and you can't switch on and off different parameters of your participants. There might be some manipulations you can apply to make them approach the task in a certain way or another way, but you have far less control over how the participants are actually solving the task. But on the upside, you know that the human participants are solving this task in the way that human participants do. So often one of the challenges of kind of selling a simulation model to an audience in a journal article or in a talk or whatever is that you have to convince them that your model of a simulated agent is relevant to how humans behave. And if your simulated agent is a human, then you don't have to do that. So people have less trouble relating one of our lab experiments involving human participants to how real human languages work, and it's often a bit more of a struggle for people to think about how this very abstract simulation, which is actually really clean, and we know exactly what's going on in that simulation, but people find it harder to relate the results of those simulations to what happens in human languages. So I think actually the simulation modelling stuff is potentially more powerful, and you should believe the simulation results more because we know exactly what's going on in those models. But it's easier to relate the results of the experiments to real human behaviour because it involves humans, basically.
Yeah, I think you're absolutely right that there can be a perceived energy barrier you've got to get over when you present the simulation data or simulation result.
And that can be extremely frustrating if you've got so we essentially get the same results in the lab and in simulation.
Okay.
But people always find the experimental results more persuasive. It's easier to persuade people using results from an experiment than it is for results from a simulation. I think that's actually the wrong way around. I think people should believe the simulation results more than they believe the experimental results, but it seems not to be the case.
Okay, so I mean we're sensible people who use simulation all the time. Why do you think that is the case? Is it because there's a certain opaqueness with regards to simulation? Because you can make a model that can do anything, right? So you just need to give it the right parameters and you'll get the result that you're kind of trying to build in from first principles. Is that part of the problem?
Yeah, so I think lots of people know have enough idea of what goes on in a psychology experiment. So you get people to do stuff and you see how they do it, right? That's basically how an experiment works. Lots of people don't have, there's not as many people who have an understanding of how simulation models work. So fewer people do simulations, basically. It's probably changing a bit. Simulations are probably a bit more acceptable than they were 20 years ago, maybe. But people have think they have an intuitive understanding of how an experiment works that they just don't get for simulations. So they're not sure of what you're trying to achieve or how you actually did it. Right? So an experiment is obvious. It's actually quite easy to run an experiment. You just get some people and you ask them to do something and you see what they do. If you don't program, then it's maybe not obvious how a simulation works. Like where do you start when you're going to do a simulation? So that's one problem. Then there's this, so people just don't know how it works, and they think you've done something sneaky, or people just aren't sure what you've done. The other thing is this building it all in thing. So people do realise that simulations aren't witchcraft, right? So you get out what you put in. If you set the parameters in a certain way, you will get out a particular outcome, and that outcome is a consequence, maybe through some really complex interactions and some kind of complex, interesting process. That outcome is a consequence of the parameters you set. So people say, well, look, what's the point in you set the parameters? You get the result that you want. You've built the result into the parameter settings. People think there's something wrong about that. But of course, the point of doing simulations is to find out what settings of those parameters get the behaviour you're interested in. Yeah. So the point is to find out what parameter settings get you that behaviour, and it's not. I mean, the whole point is that you are building in the result with the parameter settings, but it's not obvious how the settings of the parameters relate to the result. So that's why you have to run the simulation to figure out what that mapping is. But then all you care about is the parameters. So how do my agents learn? What does the task have to be to get this set of results? How fast do they have to learn? What's the population model that gets us the results we care about that mirror the results in real human populations and so on? So you're trying to find out those things via simulation. I think people are worried that you're somehow smuggling in the result by building it into the model. So that's quite a common response. We've just built that result in, of course you get that result, and that's the point.
Okay, yeah. So you're going to be talking about today, I don't know if it's fair to characterise it as competing pressures of biological or cultural evolution. I'd like to know a little bit about that, but before I do, is simulation, as opposed to the empirical experiment, is that just better placed to be able to ask these kinds of questions?
Not necessarily, right? So if you want to study cultural evolution, you can do that with a simulation model of what happens when people learn from each other and so on. You can simulate cultural evolution, or you can run cultural evolution experiments. There's a whole bunch of people studying how behaviours change over time in little lab populations, and that's something we do. If you want to look at, if you want to think about what biological evolution of communication might look like, or how genes and culture might co-evolve, might influence each other in shaping a communication system or any other behaviour, then it becomes a bit trickier, right? You can't run lab experiments on biological evolution or gene culture co-evolution, so you have to bring in some other tools to study those. So you might do a kind of comparative psychology of communications, how do other animals communicate, or you might do a bunch of fancy stuff looking at how try to figure out how genes and culture have co-evolved. So what, do you get different distributions of genetic variants in different populations with different cultures, or something like that. But another way to tackle those questions, which we can't study in the lab, is by simulation. So some of my work's been on simulations of gene culture co-evolution in communication, and we can do the cultural evolution part of that in the lab, but we can't do gene culture co-evolution in the lab. You do really need to go to simulation to figure out how those kinds of processes might interact.
Okay, so how does one, given that you're doing empirical experiments right now, what kind of questions are you asking with these kind of experiments? Okay,
so the talk I'm going to give today, we basically say what happens to language when it's transmitted in a population. So you have people who learn their language, and the data they're learning their language from is linguistic behaviour of other people speaking, but those other people in turn learn their language in the same way. So you have language basically being passed from person to person to person in populations, and languages persist in that way for tens of thousands or hundreds of thousands of years. So language has been transmitted from person to person for a long time. So the question is, given that language has been transmitted in this way, maybe it has some consequences for the structure of language. So maybe we can understand some of the kind of properties of language, like the fact that it has words and rules for combining words. Maybe we can understand these basic kind of structural properties of language as a consequence of language transmission in populations. So in today's talk, I'm going to talk a little bit about what happens if a language just has to be learned, and the answer is it gets very simple, because simple things are easier to learn. What happens if a language has to be learnable but also expressive, so also useful for communication. If you have both those pressures at play, then what you get out is structured languages. So languages that are expressive, so they allow you to make a large number of distinctions, but they do so in a very economical way. So you basically have words and rules for combining those words. That's a nice way to build a simple yet expressive system. And then you can say, well, what happens to languages if it just has to be expressive and it doesn't need to be learnable, it doesn't need to be transmitted to naive individuals? And what happens then is that the language is very expressive, it has a whole bunch of distinct words for things, but there's no recombination of words, so there's no grammar to that language. So you can say, or the conclusion I draw in the talk is that linguistic structure, so the fact that language has these complex utterances which are built by combining words in a kind of rule-governed way, that can be understood as a consequence of cultural evolution under pressure for learnability, arising from the fact that language has to be learned by children, basically, but also expressivity, so it has to be useful for us to communicate. And cultural evolution will explain some of the big structural properties of language. So you don't need to say, well, there must be some evolved biological module underpinning compositional syntax, so this creation of complex utterances by combining words. Because once you have people learning and using a language, then that kind of compositional syntax will just arise through cultural processes. You don't need to evolve a kind of hardwired module that gives you that stuff.
Okay, so if there is this notion of a trade-off between how easy a language is to learn and how easy it is to express things within the language, do you take real-day human languages, and can they be put into this kind of space of expressibility and learnability?
So surprisingly, some of them can, right? So the kind of at a first approximation, all languages are equally expressive, so they fulfill all the needs that people have for a language, and they're all learned by children, right? So they're all in the same ballpark, but nonetheless, you do seem to get some kind of, and this is new stuff, right? So this is surprising to a lot of people and slightly controversial. But you do seem to get some variation in the complexity of languages. So languages that are spoken in large, diverse populations tend to be simpler than languages which are spoken in small, isolated communities. So that's a paper by Gary Lupian and Rick Dale. They say there's this correlation between population size and complexity. And their explanation for that is that in these large populations you have a lot of adult learners, basically. So large populations, like a large language like English, has a lot of adults coming to English and having to learn it. And basically adult learners tend to simplify languages. So there might be some link between demographics, population size, and the makeup of your population and how complex or simple your language is. There's also cases of sign languages, which are so these kind of naturally arising communication systems in populations who don't have access to spoken language. They basically come up with a new language, a signed language, and you can compare signed languages which are of equivalent ages and are even in the same part of the world. So you can look at sign languages within Israel, and you see surprising differences, for instance, between Israeli Sign Language, which is spoken in a large community of deaf people, and there's a kind of diverse community and a lot of kind of coming and going of people and entry of new individuals and so on. That basically works like any other language, any other sign language. It has all the structural complexity you would expect. And then you look at an equivalent, a village sign language of the same age, spoken by in a Bedouin village. Completely different population structure, much smaller population, much more family-based, much more rigid population structure, and you see that the sign language in that kind of community is rather different and doesn't have some of the structural features that we might expect, despite the fact that it's of the same age. So there might be, that's surprising if you think that there's basically a language faculty that imposes a uniform blueprint on any communication system, but it's maybe what the kind of thing you would expect if languages or language structure was in part a consequence of or was influenced by demographic effects like population size and kind of population structure and so on.
Okay, we're going to have to finish soon because people are actually coming in to want to listen to your talk. If there is, let's imagine that's true, and there is this really interesting mechanism by which the complexity of language may change. What kind of insights or intuitions then do you have about the future of human language? Because although there is still incredible diversity with languages, I mean it's getting less and less every year, and there's an increasing trend to urbanisation, so larger and larger groups of humans. So in 100 or 1,000 years' time, would that mean we would have a simpler kind of language? Like the lowest common denominator type of language?
Not necessarily the lowest common denominator, right? So English is a relatively simple language. It has very little morphology, basically, and Chinese is also a very simple language. It's an isolating language. You basically don't do any nasty inflectional stuff on words. Words are just combined, and their form is fairly kind of invariant. So you wouldn't want to say that English or Chinese was the lowest common denominator language, right? It's a massively expressive and still very complex system for communication. The number of languages in the world is declining very fast, so languages are dying out all the time. That's a shame because we're losing interesting information about how human communication systems can work. There is, or there should be, a kind of counteracting force to this kind of homogenizing pressure. So it's not possible to have one language that's spoken around the world in a uniform way. So you and I are both speaking English, but the Englishes we speak are actually quite different, right? So even within a small island like Britain, you see variation in the single language that's spoken there. So as well as this kind of homogenization pressure, there's also diversity emerges just as a result of the fact that people are influenced by the people they hear every day, and you can't hear everyone all around the world all the time, all day. So you will get regional variation in the linguistic system. So that might kind of inject some variation back into the system. So I don't think we need to worry about there being or hope for a single worldwide language. I think that's basically impossible. But it's a shame that we are losing all these other languages that have interesting ways of solving the communicative task that differ from the way in which English, say, solves that task.
Yeah, it must be pretty tragic as a linguist to watch all this data just disappear before your eyes. But anyway, let's conclude on that optimistic note. Thanks again for coming. I look forward to the talk. And yeah, great.
Okay, cheers.